Good morning, Year 10s. How's it going, guys? Hey, everyone's in. Callista's the first in the house. Hello. Ian's like, first one in. No, you weren't, Ian. Callista beat you. Like and comment. Callista's the first in the house. Ooh. Hello. Ian's like, first one in. It's all stretched. It's very strange. Right. Let's crack on, guys. No. Amazing. Okay, guys. I'll crack on with today. So share screen. Share first screen, click on that one. There we go. Hide that. So today's lesson. Zhoosh. There we go. There we go. So we have got bonding, covalent bonding part 2. And this is, I'll actually change that. It is lesson 11 giant covalence. We can do covalent if you like. If people like it just being, I think it's probably a bit clearer if I do covalent, covalent bonding part 2, and this is the giants. Giants. I'll even make that big. Yeah. The giants. I like it. Cool. Learning objectives. 2 learning objectives, nice and easy today, guys. Know the giants. So you've got to know them. When is the homework due? Let's reach 10 likes. I know we can do it. I'm going to go through the homework now, Lauren. So don't worry. If you haven't done it, what you can do is you can pause the video now, and you can then do the homework now, and then you can watch the video back then to mark it. So I'm going to go through the homework that I set you guys now. So the 2 learning objectives today are to know the giants and explain giant covalent properties. But before that, let's run through your homework. So I gave you a quick homework of doing some dots and crosses. 2 marks for each part. So we've got methane. So our stick diagram becomes this. There's our stick. And then our dot and cross. It's actually quite tricky, isn't it? Because it's quite a tight space for the dot and cross. Oh, I definitely need to put a new battery in my pen. There we go. Dot, cross, dot, cross, dot, cross. And everyone's happy. That is it. Methane, nice and easy. 2 marks. 1 mark for that guy. 1 mark for that guy. Next, ammonia. Stick. You can do the stick however you like. If you wanted to put so the H is going up, you could have done. Didn't really matter. If you're interested to know the real shape of ammonia is this. It's called pyramidal. This is actually the correct shape of ammonia, but you don't do shapes until AS. So this is absolutely fine. This is a 3D diagram, and that's ammonia. So we can do dot and cross. Nitrogen. Can't do a 3D diagram for ammonia at that point. And this one's slightly trickier because we've got to remember to make everyone add up to 8. So 1, 2, 1, 2, 1, 2. And then nitrogen only has 6. So you put on 2 extra crosses and you're done. Check it. If you've done circles instead, that's totally fine. Totally fine. Next one, oxygen gas. So you realize that the stick diagram is super handy. Oxygen makes 2 bonds, so it's going to make 2 bonds with the other oxygen, so they're all happy. Now, this is a double bond now. So this time, because it's 2 sticks, we've now got 2 pairs in the gap. My laptop is kind of struggling. It's not on charge. So if I put it on charge, I can then crank it up. There we go. Should be a bit better. There we go. And then you need to make everyone add up to 8. Now, they wouldn't care. I'm going to do dots on one and crosses on the other. They wouldn't in reality care. Yeah, if you did all crosses or all, they wouldn't care. As long as in the gap, it's a dot and a cross for each one. Yeah, that's the only thing that really matters. And that's a double bond. Next, tick it if you got it. 2 marks for those guys. 1 for that, 1 for that, 1 for that, 1 for we already know those. I love the fact it takes a second just to load the green. Let's go for the next one. HCl. So stick diagram, nice and easy. Hydrogen makes 1, chlorine makes 1. There we go. hydrogen, one pair in the gap as a dot and cross. If you do chlorines as circles, that's fine. One each. Next, bromine makes one bond to itself. I like it. Wow, they're almost identical, those things. So dot and a cross in the gap. This guy I'll give dots, and the other guy I'll give crosses. There we go. Next, phosphine. Oh, phosphorus. I didn't give you that rule in the previous lesson, but the worksheet has the rule. I wonder if anyone noticed that. It's in the same group as nitrogen, so it makes 3 bonds. Yeah, I hope people figured that out. So it becomes PH3 like this. Right? Convert. So P, H, H, and H. Oof, that's going to be really tricky for me to put my dot and cross in that tiny gap. So I'm going to color code that to make it slightly easier. Yeah, that's okay. I understand that. I've not done it great. I'm going to do dots for this one for phosphorus. There you go. Next, CO2. This was a tricky one. Edexcel do love this at GCSE. So the stick diagram is this. It's a tricky one. Got to have two on either side. So carbon. Oh, I'm definitely going to need to redo that. Need a fairly big gap really for this one. Right, carbon, oxygen, and oxygen. And we need a double bond for each one. So dot cross or cross dot. Either way, makes no difference which way round you do it. Oxygens I'll do as circles. And these ones are now actually circles as well at this point. Yeah, because carbons are crosses. Yeah, again, they won't care as long as you got the right number in the gap. Silicon tetrahydride. Ooh, it's in the same group as carbon. It's going to form 4 bonds. Yeah, it's going to do the same thing that carbon is doing. Sticks, right, into circles, all single bonds. There we go. All single bonds. So in the gap is going to go, still lagging just a little bit. There we go. There we go, and I'm done. Water. Always like water as one of these. Again, Edexcel loves water. So it's nice to draw it with its real shape. So those people who are interested, yeah, water has the shape bent. You could also call it V. They allow V-shaped as well, but it's bent. Wonder if anyone in the class can remember its bond angle. See if you can. As a stick, as a dot and cross. So I'll do it linear. And in the gap, they won't care, of course, if you do it like that. They wouldn't even care if you actually did that dot and cross diagram at A level like that. There we go. There's water. I wonder who's going to pick up that on the chat as the bond angle. Maybe who made the note. Next, nitrogen. Tricky one. Nitrogen makes 3 bonds to itself. So that's a hard one because we need a big gap. There we go. Just to make it nice and easy for me to fit in 3 pairs. 1, 2, 3. They've all got 6 now. And then I just need to give each of them the extra 2. Tick it if you got it. Right. Oh, ethene making an appearance. Well done, Zina. 104.5. Well done. 104.5 for water. Carbon dioxide is linear, 180 degrees. Ethene. So that's a tricky one. You've got to figure out where all the bonds go. Carbon's got to make 4. So it's got to be a double bond between the others. Next, so that becomes dot and crosswise. Kind of get used to doing them after a while. And then in the gaps, this one's a bit tricky because you've got a double bond in the middle. So we've got 2 pairs in that gap, but only 1 pair in each of those gaps. And actually it all adds up at that point. Everybody's got 8 and 2, which is good. Next one, ethine. I gave you this one in your lesson, which is really nice. Yeah, ethine. Yeah, eth, by the way, this is ethene, just to color coordinate this. Eth means 2 carbons, and ene means double bond. This one is eth. This one is ethine. And once again, the eth is for 2 carbons, and the ine is for the triple bond. It's nice to know that. Yeah, it's just nice to know. Dot and cross. Whoa, need to flip that over. Oh, no. It's only 2 hydrogens. There we go. I've made it slightly bigger now so I can fit everyone in the gap, because I need to do a dot and cross for that guy. That's easy, 1 bond, but then I've got 3. There we go. And I think everyone there adds up. So we're done at that point. Ethine. Tick it if you've got them. Next one. Ooh, blimey. Okay, this is hard. So there's lots of options here, guys. The actual real answer is this. I should have given you the name with this. This is the real answer. But I did accept a whole load of others as well. So you could have done that one. You could have also done this. Put the 6 in a row. And then done that. That works out as well. Could have done that. Did anyone get this one? Hard, that. This is called benzene. Yeah, this is called benzene. So then the dot and cross. Wow, what a mess this is going to be. So the dot and cross. Oops, that wasn't very good, was it? Carbon, 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 H, 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 and H. Right, so some of them have, I'm going to do this in red now, so some of them have double bonds, so I'll do this one as a double. I'll do then this one as a single, then this one as a double, and then this one as a single, and then this one as a double, and this one as a single. There we go, and then they're all 1 and 1. Hard, that. But I'm actually not going to include that one on the, I won't bother including this last one here on the marks for this sheet. So this is an advanced extension. This is advanced. So we can ignore that one from the mark scheme, but if you did it, excellent. So the marks are out of 6 for the first bit, and then 2, 4, 6, 8, 10, 12, 14, 16, 18. So it's out of 18 for the second bit. So total 24. It's out of 24. Give me your scores on the doors, please, guys. You can add your scores to the score sheet. Nope, that didn't work. Score. Oh dear, it's vanished. Score sheet. Oh no. It's not appearing. Oh, that's really irritating. Gonna have to track it down now. You can add it to the score sheet, guys. Add your scores out of 24 to it. Right, on to today's lesson. So, the giants. The giants. Okay, so the first thing I need to do today is tell you a very important fact about my bonds. So far we have seen in terms of bonds, we have seen ionic. Now you wouldn't call that bonds, it's the electrostatic attraction. Electrostatic attraction between oppositely charged ions. Positive and negative. It's that one there. Yeah, it's that force there. I don't even like doing it as electric. I'm going to do that one there. Then we had metallic bonds, which is the elect-stat attract between the C of D, the cations, and the C of D localized electrons. Yeah. So we've been looking at all of these different bonds so far. Switch to green. So there's the ionic one. There's the metallic one. Yeah. And now we've come across covalent. And covalent bonds, covalents are the elect-stat attract. They're all the same thing, aren't they? The electrostatic attraction, but between different things, between a shared pair of electrons and the nucleuses of 2 atoms. Yeah. Now, just to tell you that these ones here are the strongest ones I own. This is an important fact. Covalent bonds are the strongest of all the bonds are the strongest. Are the strongest bonds. Now, can I just tell you, actually, it's a bit more complicated than that. In reality, different bonds have different strengths. Covalent bond strength depends on its length. So if you have a short bond, so the carbon-hydrogen bond, this one here is short. This is a short, strong bond. This is very strong. Yeah, short, strong bond, very strong. About 412 kilojoules per mole. Don't ask. I'm just giving you it. Is it more than that? It might be 436. I always get my bond strengths wrong. It's over 400. It's very strong. Yeah, but if you have something like a carbon-chlorine, carbon-iodine bond, it's much longer. Yeah, longer bond, so weaker. But it's still very, they're still strong. Covalent bonds are really strong. Yeah, they are the strongest of the bonds. Now, what this means, and by the way, this is I need you guys to make sure you understand that this, I need you to lock this down. Covalent bonds are incredibly strong, like me, like Mr. Duncan. I'm very strong, me. Yeah, I'm like a strong man of BSKL. Yeah, very strong indeed. Yeah. So what that means is, what we realize is that this should infer a property. If you have the strongest bonds, what property would this usually, property or properties could we predict? Predicted properties. Does anybody want to contribute on the chat? Predict. What properties would we have based on them being the strongest bonds that I own? Just give you guys a little bit of time to think about it. It's always nice to do that. I know that everyone's like filling in the score sheets and marking homework. I totally get that. Oh no, I've got too much cream in my hands. High boiling point and melting point. Well done, Lauren, you star. Good job. Top property there, Lauren, well done. They are not easily malleable. In fact, Julius, they are the opposite of malleable. What was that word, Julius? Well done, you're right, but you wouldn't say that they're not malleable. You'd say that they were something else. What would you call them if they're not malleable? What's the opposite of malleable? I told you in high carbon steel. Brittle. Well done, Julius. Great job. They are brittle. What else? What about their strength? Would they be hard or soft? Can I just point out, well done to you two. Lauren, Julius, commendation, well done. Great answers there, good job. So top property. High, notice my capitalization. High melting point and boiling point. Well, tap device to enter. Oh, it's telling me that my pen has actually died and then it's been kind of, so obviously I need to recharge it. I do have some spare batteries in my bag, but I don't know if they're charged. Well done, it'll be very hard. Good job. High melting point. Number 2, they would be brittle. I'm going to put that as number 3. They'd be very hard. Very hard. And number 3 is they'd be brittle. Right. So, now if these bonds are the strongest bonds I have, Julius, if these are the strongest bonds I have, can you guess what substance is going to be purely covalent? Covalent bonds only. Yeah, the strongest bonds I have, the most brittle, but the most hard, and with the highest boiling point. Can anybody tell me where I'm going with this? So the answer is diamond. The giants. Okay, guys. So I'll explain this term giant to you. So there are, in the world, there aren't many of these. These are relatively rare. There are substances out there which are made, diamond. Let's go for diamond. Take a picture of a diamond, because I like diamonds. They're pretty. They're very pretty. Look how beautiful they are. They are pretty. I want a real one, though. It looks fake to me, that. Let's give it that one. I'll do. So, diamonds are beautiful things. Is it the diamond lattice structure? Yes. Paste. So, diamonds, if you look at their structure, number one is they are what's described as giant covalent structures. So diamond structure. So images, there we go. So the diamond structure is an enormous structure where all of the carbon atoms are joined to each other. It is pure carbon and all the carbon atoms are joined together in a giant structure. It's not enough this, because what you want to realize is that these pyramids, these structures go on indefinitely with millions and millions and millions and millions and millions of carbons. And every single one of them is bound to each other by covalent bonds. It is pure covalent. You don't call it pure though, you call it giant. So I'll take the picture I like, which is, I quite like that one, although I don't quite understand what the little bits are that are there. I'll go for this guy. Maybe that looks pretty good. Now, guys, I know you can attempt to draw it if you like. It might be better just to print a picture off of diamond structures. Diamond structure. So it is a giant. So what we're now going to do is, we're now going to do an exam question. And the exam question says, explain the high melting point, the high MPT. Now remember, whenever we see this question, whenever we hear explain melting point, we're running the same process. Susan Boyle sings Nelly the Elephant. Right. So what is the structure? Diamond is a giant covalent lattice. Bonds. Between carbons, carbon atoms. What am I doing? Between carbon atoms are only covalent bonds. Strength. Covalent bonds are incredibly strong. Covalent bonds are very strong. Like Mr. Duncan. Number of them. Oh, well, millions. It's giant. There are millions and millions and millions and millions of these. There are millions of covalent bonds. Lots of energy needed to break high melting point. So we realize what the structure is. In order to melt this, I'm having to break him. You get the point. Like, I've got to break every single one of these covalent bonds, and these covalent bonds are tough. That gives diamond a 4,000 degrees Celsius melting point. Like, seriously? What? That's insane. Diamond be crazy. Now, if they asked you to explain diamond being brittle or hard, you actually do exactly the same process because the reasoning is the same. It's a giant covalent lattice. Carbon atoms are held together by only covalent bonds. Covalent bonds are very strong. There are millions of covalent bonds in the structure. Lots of energy needed to break. That's what makes it hard. Yeah, they're rigid. They're strong. Everyone's bonded together by these crazy strong bonds. So in my first learning objective, I said you have to know your giants. So what other giants? What about the electrostatic attraction? Yes, that's a good point, Lauren. In reality here, you don't actually need to explain the electrostatic attraction here. It's done. In this one, yeah, you only need to say covalent bonds. You do that with when you have the ion. So the difference, this is why you have to learn stories. Sodium chloride, there's no real bond there, remember. That's why you have to describe the electrostatic attraction, because they're not actually joined together. Yeah, this is an electrostatic attraction between these two. So we would say structure, this is a giant ionic lattice, bonds, the electrostatic attraction between oppositely charged ions, and the strength is very strong, and the number is millions, yeah, and the energy is high, yeah. And then if you have metals like magnesium, the next story, so describe the bonding in magnesium, we'd say Susan Boyle sings Nelly the Elephant. This is high melting point. Structure, it is a giant metallic, a giant lattice of cations surrounded by a sea of delocalized electrons. The bonds is the electrostatic attraction between cations and electrons C. The strength is strong, number millions, energy high. I know it's tricky, this, and you have to learn these stories, Lauren. You learn a different story for ionic, metallic, and covalent. There's another one here for simple covalent in a minute, which we're coming to. So I need to go back to the giants. I hope that was helpful, Lauren, giving this like summary, this run through of each of them. Anyway, so what other giants are out there? So know your giants. So number one is diamond. I put diamond, nice, diamond. Number one is diamond, pure carbon, carbon solid. Number two is graphite. Now, graphite gets its very own lessons. Yeah, graphite is also carbon solid. These two are said to be allotropes of each other. Allotropes. It's allotropes. It's tropes. Allotropes. Got to Google that. Allotropes? Yes, allotropes. Graphite gets its very own lessons. This one here, so graphite, yeah, see next lesson. Gets its very own lesson, graphite. Number three is sand, otherwise known as silica, otherwise known as silicon dioxide. Silicon dioxide, otherwise known as quartz. Isn't that crazy? And that's SiO2. Silica, sand, quartz, silicon dioxide. It's right. Oh, thanks, Zina. Number four is silicon. Silicon as an element. brackets Si. It's in the same group as carbon, group 4. It does exactly the same structure as diamond. And it'll be interesting to compare those two. And then number 5 is titanium dioxide, TiO2. I'll write down the name. Titanium dioxide, TiO2. So, and that's all you need, folks. Those are, the graphite's a bit different, and we'll look at graphite separately because it requires a little bit of extra, but that's all you actually need in terms of the giants. Yeah? And if you look at the structure of each one, they're very similar. So, except for graphite, which is standout different. So, titanium dioxide's different as well, but we can argue that diamond, each carbon atom makes 4 bonds in this funny pyramid-like structure. In silicon dioxide, it does the same thing. Silicon, oxygen, silicon, oxygen, silicon, oxygen, silicon, oxygen, silicon, oxygen, silicon, oxygen, silicon. They keep, it has a very similar structure. They all do this, they all do this really cool pyramid-like structure. So sand does it too. Let me show you. They can draw it better than I can. Yeah, SiO2 structure. Nice. And there it is. Same diamond-like pyramid. Nice to see it. If you look at silicon, it's the same as diamond. Same structure. It's not giving me a nice image. Same pyramid structure as diamond. Same thing. So we can compare these guys directly. They've all got crazy high melting points. Diamond, 4,000 degrees. Graphite, 4,000 degrees. Sand, 1,600 degrees. Silicon, it's one of them is 18 and silicon. One of them is 18 and one's 16. Silicon, I'll put melting point. Silicon melting point is, it's not helping me. Oh, come on. Doesn't help me at all. Silicon, melting point 1,400 degrees. Titanium dioxide, holy moly, that's going to be high. TiO2, whoops. TiO2 melting point, it's not helping me. It's not helping me at all. Titanium dioxide, Wikipedia, give me the melting point. Melting point 1,800. Crazy high. All these are in Celsius. So they're all crazy hard and crazy high melting points. And these are our giants. And this is because the only bonds to break are covalent. That's all. These are pure covalent. They are said to be giant covalents. And the answer to all of these melting points is the same, which is this. We just run that process. That actually brings me to the end of my lesson today. I'm going to end there. Oh, one more thing. None of them conduct electricity. Yeah. Except graphite. It's special. Yeah. So diamond, silica, sand. Yeah. Silicon dioxide, pure silicon's a bit tricky because it's a metalloid. It's a bit weird. TiO2, yeah, do not conduct electricity. Do not conduct electricity. And the reason why? No, why, question mark? red, no free electrons. No free electrons. All electrons locked up in bonds. We're done. That brings me to the end of our lesson today. Anyway, I'll leave it there, guys. Right, I will end my lesson there. I hope you found it okay, guys. We've got our giants. We know our giants. Next lesson, simple covalent, which is a bit more tricky. And I'll see you guys tomorrow. Take care, guys. See you later.